Hey AP Chemsters, this is Mrs. Vanderwille bringing you another edition of the Blankwalle series. Today we're doing section 16.4. It says titrations and pH curves. Again, I cannot emphasize enough how important this section is and how I'll pretty much guarantee that this will be on your AP exam in some form. Typically, this is a free response question, though it doesn't have to be. But this is a very important section that you really do need to pay attention and focus on. So once again, I'll start off telling you the same thing as always. Make sure you have your calculator with you. Make sure you're actually doing the calculations with me. When I say to pause, go ahead and actually pause it and actually carry out the calculations. Don't just watch me do this. You will learn a whole lot more if you're actually doing the work yourself, okay? Also, make sure you're jotting down any questions that you might have as I go along that Mrs. Blankenship or I could answer the next day in class, okay? So having said that, let's see what we're talking about. Titration is, by definition, the controlled addition, usually by a pipette, not a pipette, I'm sorry, a burette, of a solution of known concentration, which is called the titrant, in order to determine the concentration of a solution of unknown concentration. That is a traditional titration curve. We're going to see on later on in lab, in a different lab that we're not doing tomorrow, but a different lab, where we will actually have a known concentration of both the titrant and the other value, the other acid or base. And here we're going to actually determine like the halfway equivalence point and the equivalence point. So it doesn't have to be of unknown concentrations. Very typical, but not always. There's something called equivalence point, and hopefully the word equivalence jumps out at you. Something has to be equal at an equivalence point, which is also known as a stoichiometric point. And what is that? That's equal to moles acid equals moles base. Hopefully you remember that probably from when you had chemistry the first year, that you probably did an acid-base titration. Where you actually went through and found this equivalence point. An indicator, again, is used. It is a substance which goes to undergo a color change to indicate when this equivalence point is reached. We can do a lot of math with that. It's where you can say moles acid equals moles base. You can solve for molarity, if you will. Anyway, so we're going to talk about indicators a little bit later. And then we're going to be plotting a titration curve. And a titration curve is where you're plotting the pH of the solution. That'll be your y-axis, and then the volume that you are adding of the titrant is going to be your x-axis. And so we're actually going to go through a sample one of these, and you're going to see how this all kind of works out. So let's take a look at the first example. So the very first case here is a titration of a strong acid with a strong base. This is very common if you have hydrochloric acid and sodium hydroxide. This is probably the reaction that you did when you maybe had your first titration in your first year chemistry class. Very, very common. So notice I have a 25 ml sample of hydrochloric acid, which is 0.1 molar. And here I do have a known molarity of sodium hydroxide. And what we're going to do is that we are going to titrate this 25 mils of 0.1 molar hydrochloric acid with different increments of sodium hydroxide. And our goal in this section is actually to determine the pH of this solution after adding your different quantities of sodium hydroxide. So really the first thing you ought to do is, it's important to know, when do we reach the equivalent points, at what volume, and we're going to see later on why this step is actually very important. So go back through, when you reach an equivalence point, what did we say is true? What's equal? And we said that moles acid equals moles base. So we're going to actually calculate then what are these moles acid and moles base. So if you recall, moles acid, if you draw out your triangle, if you will, moles are on top of the mountain. And so moles is equal to molarity times liters. And so we can actually plug in that equation. The molarity of my acid is up here at 0.10, so there it is. My volume, notice what I had to do with my volume. Because we're dealing with moles, I had to convert my milliliters into liters, and then I multiplied. So that's how many moles of hydrochloric acid I will have throughout this entire process, okay? That I will always have, to start with anyway, that many moles of hydrochloric acid. And now we need to figure out how many moles of base we have. Well, what's true about the equivalence point? Moles acid equals moles base. So if I have 0.00250 moles of hydrochloric acid, guess what? I have 0.00250 moles of sodium hydroxide. And finally, my whole process for this part A is how much volume of base does it take to reach this equivalence point? Well, liters is equal to moles divided by molarity. And I know that from the step above, I have this many moles of sodium hydroxide. I know right up here, I have 0.100 molar solution. And when I put this all together, whoops, and so if you do your division, you end up with that many liters, and I just convert it back to milliliters. Now, it shouldn't shock you that this volume is actually the same as the volume of your acid. Why would those volumes be the same? Well, look what happens. Our molarities are the same. So if you want the same number of moles and you have the same ratio of molarities, then you're going to have the same volume. We kind of talked about that in section 16.3 in a sense. So hopefully that makes sense to you. Let's go on to the next page. You'll notice we have a graph here, and this is what the graph we're going to continue to keep using to plot our pH curve. Okay, so we're going to be flipping our pages back to here and adding there. So that's our curve here. So let's go on and do some more math. So our goal here is, as we've done in many problems, what is the initial pH of this solution before we add any base? So I put this equation here where HCl, single arrow, goes to H plus Cl minus. First of all, why is it a single arrow? What do you know about hydrochloric acid? Well, yes, it is a strong acid. And the single arrow also implies what? That this strong acid is going to do what? It's going to 100% dissociate. So however many moles of HCl I have, well, guess what? That's how many moles of this H plus the hydronium ion we have. And why is that the case? Well, because HCl is a strong acid. That's why. So it's 100% dissociation. So what is the pH? Well, we're just going to plug in our equation. pH is a negative log of the hydronium concentration. So it's a negative log of 0.100. And the pH then is equal to 1. Okay, so what am I going to do next? I'm going to find the plot of the pH versus volume. It says it's already been done for you, so let's see how that works. So at 0 volume, I haven't added any base yet, our initial pH is 1. Okay, well, let's go on. It says, well, before the equivalence point, and that's why we had to find that volume. So it says that at, before the equivalence point, the hydronium ion can be calculated in how I'm going to show you. And if you know the concentration of the hydronium ion, you can find the concentration of the pH value. So when moles acid is greater than moles base, so this is for any volume less than the 25 mils that we showed on the prior page. And so I wrote, this is why you calculate the equivalence point first, that you will know that if you have any volume of a base before 25 mils, then you're going to have more moles of acid than moles base. So let's see what we do. Okay, so again, we are adding a base to an acid. And as we did back in chapter 4, this is actually a stoichiometry problem. So it says when adding an acid, or in a case in a buffer, in a buffer, what question did I ask? Well, it was, what will it react with? Okay, it's a similar question. So if I add hydroxide in the solution, what is it going to react with? It's going to react with the H3O plus. It's not going to react with the water, I'll tell you that. It's not going to react with the chloride ion. It's going to react with the hydronium ion. So because this is stoichiometry, we need to set up, yes, your favorite, the BCA table. So the B stands for, of course, before. Notice that we've already calculated how many moles of the hydronium ion we have. That was on the prior page. You're going to find out that this number never changes. Okay, so for the B, why? Because that's our initial amount. That won't change initially, but it is going to react, and we're going to find out that the change is going to be a different number, but we're going to start off with 0.0025 moles. And then what do? We are adding a certain amount of base. Now the question is, all right, how much base am I adding? A BCA table has to be in moles, but right now I only know I have 5 mils of it. So I actually needed to calculate how many moles of sodium hydroxide I have. And so, of course, you should know this. Moles is equal to molarity times liter. I know the molarity, and again, this isn't going to change. This is going to be the same number we're going to use over and over again. But this 5.00 mils is 0.005 liters. Again, you have to be in moles, okay? Or I'm sorry, in liters, so you can find moles. And so this is how many moles of sodium hydroxide I put into the system. So once I've calculated moles, I can now do this. I can tell you how much I have added to my system. So I'll just kind of stick it like that. So I've added 0.0005 moles. Now what's going to happen? This many moles is smaller than this many moles of the hydronium ion. So when I do my BCA table, what's going to get used up? Well, hopefully you figured out mathematically that it's the 0.005 mole or 0.0005 moles. So I'm going to subtract, and obviously when I subtract these two out, they're going to become 0. But how many moles of the hydronium are left over? It's 0.0020 moles left over. And so this is now our new moles of hydronium. Now look at my step 2. It says a strong acid, strong base does not need an ice table or the HH equation. Is this an equilibrium setup? Now the answer is no. This is not equilibrium. This is strictly stoichiometry. So this is the key number that we're going to be looking at. I really don't care how many moles of water I have. It's not an equilibrium setup. I don't have a buffer setup. That's going to come later. But for right now, I don't have any of that. So I do not need any of this setup. I just need to find out what the hydronium concentration is. Well, I know it's moles per liter. And I'm going to say, careful, careful, careful here. Why careful? Well, I'm going to use this many moles, but look at my volume. This is the initial volume I started out with, 25 mils of the hydrochloric acid. But if I were to look at my beaker, the volume in my beaker where the hydrochloric acid started with, I added more volume to. I added 5 more mils. Where'd that come from? This right here. So when I add 5 mils of sodium hydroxide, I'm now changing my volume. So now I have 30 mils in my beaker, which is 0.030 liters. So why don't you get your calculator and finish this off? What is 0.0020 moles divided by 0.030 liters? And tell me what you get. Okay, hopefully you got this. And now go ahead and hit your log or your negative log button and find the pH. Okay, hopefully that's what you got. So what does this tell me? I've added some base. The pH went from 1 to 1.7. That should make sense to you because the pH is going to go up with all the additional base we've added. So what am I going to do now? I'm supposed to plot the graph of pH versus volume of sodium hydroxide added. So let's go back up here again. And I have added 5 mils. If you look, this is 5, 10, 15, 20, 25. So each one of these is 5 mils. And what happened to my pH? It just went up a tad, didn't it? Here's my pH. It didn't change a whole lot. It's just up a little tiny bit from that 1.0 we started off with. Okay, so that's my first value. I'll even put a little 5 here. That's my first value. Okay, all right, we're going to do this again. This is so much fun. Oh, I think I have to turn the page. All right, let me turn the page. All right, so let's try another increment. I am going to add a total of 10 mils of sodium hydroxide. Well, what do you think the first thing we really need to know? Well, if I'm going to set up a BCA table, I need to know moles. So go ahead and calculate how many moles of sodium hydroxide you're going to add. So pause this, calculate. Okay, hopefully you got 0.0010 moles of sodium hydroxide. So what is my first step? Well, step 1, I'll put that right here. Again, what's going to happen to your sodium hydroxide? It's going to react with all your H3O+. Okay, now we can set up our BCA table. Oops. So here is my B. And once again, I have the same number of moles of the hydronium ion that we start with. This is my initial setup. But this time, I'm going to add 0.0010 moles of sodium hydroxide. And here's my change. So I'm going to use up all my sodium hydroxide. And I guess this is a little shifted a little over. But you can see that this is going to be 0. And I guess maybe I can do that. And so what's going to happen to my hydronium concentration? Well, I'm going to lose some moles. It's going to make it neutral water. And I'm going to end up with, you guessed, no moles of sodium hydroxide, but 0.0015 moles of my acid. So there we go. We've used up some more of the acid and to make neutral water. And now our step 2 is to find the pH. So why don't you go ahead and pause this and calculate pH on your own. Well, hopefully you figure this out, or at least you're trying to. That effort is always important. So the hydrogen ion concentration is moles over liter. Again, why am I telling you to be careful? What am I trying to have you think about? What is in that beaker? We start out with 25 mils of the hydrochloric acid, but now we've added 10 mils of your sodium hydroxide for a total of 35 mils. But I have to convert that to liters, and there you go. Here's my molarity, and there's my pH. Again, does this pH make sense? I sure hope so. Why is that? Because my pH keeps going up. Not by a lot, but by some. So now what do we want to do? We need to plot the point. So turn your page, go back to the graph, and let's plot the point. So when we plotted the 10 mils of sodium hydroxide, what happened over here? It went up just a little bit. So I put it up just about 1.37, 1.4. You can tell it's not exact, but it's pretty darn close. All right, let's go back and see what happens next. All right, so now I'm going to add 15 mils. So what was our first step the last time? Actually, this isn't the first step. What did we have to do? What goes in the BCA table? Well, if I actually know that I start off with this many moles of hydronium ion, what do I have to calculate here? I have to calculate the number of moles of hydroxide. Well, how do I do that? Same as always. Okay, we know the molarity, know volume. Plug in your numbers, and that's how many moles of hydroxide I've added. So I'll say that right here. That's how many moles of hydroxide I've added. So now what? What do I have more of? I have more H2O positive. I have less hydroxide. So I'm going to use up all my hydroxide. Oops, sorry, wrong one. Here we go. And here is my setup. So what happens to hydroxide? It's going to equal 0. What's going to happen here? It's going to equal, I did that again, didn't I? And here it is. Okay, why don't you go ahead and solve for the hydroxide concentration and so the pH. Go for it. All right, no peeking. You should have this done before you see my version. All right, so what do you get? You have moles per liter. We have 0.0010 moles. Again, that's this number right here. That's how many moles of acid we have. But notice my volume keeps changing. My volume keeps getting bigger. So I had to add the 15 mils that I added right here. So there's my 15 mils. Add that. I get 40 liters or 40 milliliters. And convert that to liters. I do the math. And there's my molarity. And here is my pH. So what do you notice? Does this make sense? If you keep adding more and more base, your pH is going to go up by a lot, not by much. Let's go to the next page, or turn back to the front page there, and let's plot this point. All right, so let's put it maybe like in through here. And I think we got one more to do. So why don't you do this problem all by yourself? Okay, so start from the scratch, calculate your moles, calculate your molarity, and plot your point. Let's see how you do. Here's all my work. Why don't you check your work and see how you did? Okay, so let's go plot the point. And it's almost close to 2, isn't it? So I'll plot about right up here, 1.95. So my pH is going up, not by leaps and bounds, but it's going up. But watch what happens next. So we are at the equivalence point now. We've added 5 more mils, so now we're at the magical 25 mils that we talked about before. And we said the pH at the equivalent point of a strong acid and strong base. Not always, 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 but in this case will always be 7. Why is that? Well, if I start off with this many moles of hydronium, I add 0.0025 moles, I've added the same number of moles. What has happened? All my moles of hydroxide are used up, all my moles of hydronium are used up, and what's the only thing left? Well, it's water. That's the only thing left here, and what's the pH of pure water? It's 7. Look what happens when you plot this on the graph. So at 25, look what happens to pH. Wow, what do you think is going on here? We are slowly changing, and then all of a sudden it goes up. All right, so I guess the question is, what if I keep adding hydroxide? What do you think is going to happen? Did you say the pH should keep going up? Yeah, it will be. So what will that curve look like? Is it just going to go up like this? Is it going to go up like this? Is it going to go down? What's going to happen? Well, guess what? We're going to find out. Let's turn to the next page, okay? So what does it say? Now that we've reached the point of the equivalence, what happens after we go to the equivalence point? It says that hydroxide can be calculated from excess hydroxide in the volume of the new solution. So the hydrogen ion concentration, the pH, can be calculated from the hydroxide and Kw. We're going to set up and see what we're doing. Again, some things don't change. What's the first thing we find each time is the moles. What's our first step here? We have to use stoichiometry. We start out with, again, 0.00250 moles, but now we've added this many moles. What can we say now? Which is a bigger number, the hydroxide or the hydronium? Did you say hydroxide? So what am I going to subtract? Did you say the 0.0025? So now what does it mean? All of this is going to be used up. And what does that mean? I'm going to have leftover hydroxide. Did you hear what I said? We're going to have leftover hydroxide. So how am I going to find the pH? Well, pH is a negative log of the hydronium concentration, but what do you think I'm going to solve for first? Because I don't have any hydronium ion concentration, what's the only thing I can solve for? Well, what's the only thing I have left? It's the hydroxide. So let's plug in these values. So here's my moles of hydroxide this time. See that? And look at my volume. I'm now at 55 milliliters, which is 0.055 liters. I'm going to do the math, and I do this. And now notice what I'm going to write here. Careful, careful. So when I take the negative log, what am I finding? Did you say POH? That is correct. So POH is equal to 2.04. So what will pH equal? 11.96. What do you think I'm going to do now? Oh, let's plot the point. So notice, with 30 mils, just 5 more mils, what happened to pH? It shot up to, what was that, 12? No, what was it, 12 point something? I've already forgotten. Let me go back and check. It was 11.96. So actually this spot right here turned out to be pretty close. So there's the continuation of my line with, oh, I'm sorry, it's over here. With 5 more mils, look what happened. Let me try to erase that. It shot right up again, didn't it? So there's my point with a little bit of curve, but at 5 points there, or 5 more mils, you'll see it ended just under 12. All right, I think we're going to add some more and see what's going to happen. Is it going to kind of curve up like this? Is it going to curve like this? What's going to happen? Let's find out. All right, well, I'm going to let you do this on your own. See how you do. So pause this. Please work this out on your own. And when you come back, the answers will be here. So go ahead and pause this, work it out. Here's all my work. Hopefully that's what you got. I got that many moles. I set up my BCA table. I subtracted, notice all my H pluses canceled out. I got 0.0010 moles left over of my hydroxide. So that's why I'm starting off with my hydroxide moles per liter. It's my moles. Notice my volume keeps going up. There is my hydroxide concentration. So I found my POH next. That's why I gotta be very careful. Please, I've said over and over again, always be aware of what you are solving for. So label things, okay? So because we have hydroxide left over right here, we are fine. This is your hydroxide concentration, so this is your POH. Subtract that from 14, there's your pH. So let's go ahead and plot the point. All right, so a 35 down here, so this is your 35, and it end up being, well, just a little bit over 12 and a fourth maybe, so maybe someplace right here. So it's not as a drastic change. We're starting maybe to level out a little bit, and let's try one more. All right, so I think you're getting the point here. We don't have to do every single increment. Just do one more, and will you please work this whole thing out on your own, but using, note, 50 mils of sodium hydroxide. So go ahead and pause this again, do all the math, and see how you did. All right, hopefully this is how you did it. Notice that we used up all of our hydronium again. We have a lot of moles left over, we really do. Here is our setup, here is our concentration, here's our POH, and here's my pH. Did that change that much? Now I have double the amount of hydroxide, and really the concentration is not changing all that much, or assuming the pH is not changing all that much. So let's go ahead and do our final plot. So, oops, let's scroll it down a little bit. Here's my 50 mils, and I'm still just about 12 and a half, so maybe just over here. If you recall, this is about 12 and a fourth. I just went up another half of a pH with the addition of all that additional hydroxide. So it didn't change a whole lot once again. So this is a very traditional looking pH curve. So let's go to that next page and put this whole thing together. Okay. Okay, so this is an overall pH curve. This is a summary of what was just done. And I think Jonathan is here to help us out because I don't know if you see a similarity here. If I put, let's see here, doesn't it kind of go up and over, just kind of like what Jonathan's doing there? Yeah, that's, so Jonathan kind of looks like a pH curve in a sense. What do you think? All right, probably not. All right, so Jonathan, thanks for your help. Why don't you go back to where you were, and we'll call on you again. All right, so back to this again. Let me kind of erase Jonathan's curve here. All right, so here we go. Let's see here. So this is, again, strong base and strong acid. This is really important that you keep this straight. Notice that before the equivalence point, the pH didn't change a whole lot. But man, look what happened. As soon as we got really, really, really close to that equivalence point, it shot right up. Zoom, okay? The pH is at 7 with a strong base and a strong acid. And then after the equivalence point, we have excess hydroxide. And notice that we're in a very, very high pH range. And it doesn't, again, change all that much, okay? Probably if you just totally flood your system, you're going to max out at 13. Why 13? How did I know that? Well, what was the concentration that we had to start with? We had 0.100 molar hydroxide. So if I were to take the negative log of this, you get 13. So the maximum this is ever going to get to is about up to here. And that's probably if I put like a whole liter in or something. So that's our titration curve, but that's not the only one out there. Oh, sorry, we can summarize the trends. You can probably read, I just pretty much said that all this. We've done all this, but it's a nice summary. But anyway, we have more out there. So what if we have a strong base titrated with a strong acid? The other way around. I have a known quantity of a strong base, and I keep adding small increments of a strong acid. So take a look at this curve, and take a look at this curve, and jot down some of your ideas of similarities and differences. So why don't you pause this, look at it closely, and think about what's going on. So hopefully you've had some opportunities to come up with some ideas, and maybe if you come up with others than what I come up with, we can discuss those later. Similarities I came up with is the equivalence point. Number one, it is at 7. Another thing is that it's a very, very small change over here, very small change over here, a huge change right there. It's really a mirror image, isn't it? Differences. This is where I come up with some more. Where do we start? We start off at 13. Why is that? Because we have only base in here. So this is going to be a very, very basic solution. Notice that until we hit the equivalence point, my pH is in the base range. Okay, so we start off as a base, but the pH keeps dropping as you add more and more hydrochloric acid. Once we hit the equivalence point, the pH continues to drop until we get close to 1. Again, if we flood the whole thing, and so we have mostly like a whole liter of hydrochloric acid, then the pH would be probably with sig figs equal to 1. But that's about it. So again, notice another difference. What's down here, the volume of the hydrochloric acid is being added. So it's going this direction when you add acid. It is going this direction when we add base. Okay? All right. Well, this is a good stopping point. I will stop part 1 of this section. Again, this is a very long section. And what we've gone 31 minutes. Take a deep breath. Jot down your ideas if you need to, and start up with part 2. Take care.